All right, chemistry classes, how are you guys? We're going to jump right into this lesson. I would like you to pause the video now and try to answer these three questions. So go ahead, try that. All right, welcome back. So hopefully you had a minute to take a look at this. It says the melting points and boiling points of five different substances at standard pressure are listed on the table below. So you have five substances right here, these five. They're all at standard pressure. We'll talk about what that means. And they give you the melting point and the boiling point in Kelvin. Now we have these three questions. How many of these three questions can you get right? Can you scratch and claw to getting one or two or maybe all three of them right? Let's see. All right, number 54. Identify the substance in this table that is a liquid at STP. So the first thing you need to know is that STP stands for standard temperature and pressure. So everything that we see here is at standard pressure, according to the question. Okay, so everything's at a standard pressure. So we're not going to be focused too much on pressure. But we do need to know what standard temperature is. Standard temperature is 273 Kelvin. Okay, and that is on the front page of your reference table. We've definitely talked about that at times with the periodic table unit when we talked about whether things were solids, liquids, and gases at STP. But in case you forgot, it's right there. Standard temperature is 273 Kelvin or 0 degrees Celsius. But since this question is dealing with Kelvin, we're going to stick with Kelvin as our unit. So going back here, once you know that standard temperature is 273 Kelvin, there's still one big intellectual jump you have to make to get number 54 right. And that takes a little bit of work. So what I'm going to do is I'm going to try to draw it over here. What we're going to do is we're going to sort of map out a hypothetical situation where we look at a melting point and boiling point of different substances and to see what that means for solid, liquid, and gas. So I'm going to draw this little line over here, these lines over here, and I'm going to do this. Anything below a melting point, I'm going to make this first line my melting point. Anything below a melting point will be a solid, right? If you're below the melting point, you haven't melted yet, you're going to be a solid. So anything below that temperature, that melting point temperature, will be a solid. Anything that's more than the melting point, but not to the boiling point, is going to be a liquid. Okay? And lastly, anything above the boiling point, well, if it was a liquid, it's since boiled, so anything above the boiling point will be a gas. And once you have this framework set up, this question starts to take shape when it's not terribly difficult to understand. But setting it up like this can be a big jump. So here's what we're going to say. If you're a liquid at STP, right, that means that we have to, in order to be a liquid, the melting point has to be above 273 and the boiling point has to be below 273. So in order for this to be a liquid, right, the boiling point has to be above 273 and the melting point has to be below 273. So which one of these qualify? Well, let's just go one by one. HCl. So HCl melts at 159. So that's going to melt at 159. Sorry, it's going to be really ugly here. So at 159 Kelvin, it's already melted and turned into a liquid, right? And then according to this data table, it boils at 188. So 188 would be the boiling point. That means at any temperature above 188 Kelvin, it's already a gas. And 273 is above 188. So HCl, according to this data, HCl at 273 is a gas. Right? So that's not going to work for us. That's not our answer. That's not a liquid. I'll do one more, then we'll just cut right to the answer here. Similarly, if you looked at NO, right? Its melting point down here would be 109. So it's already turning from a solid to a liquid at 109 Kelvin. And then it goes from a liquid to a gas at 121 Kelvin. So anything more than 121 is a gas, and 273 is more than 121. Therefore, that can't be right either. F2 follows more of the same. Now, this one looks something like something we can talk about. Let's look at Br2 and I2. So Br2, it goes from a solid to a liquid. It melts at 266 Kelvin. Okay, 266 Kelvin. So it goes from a solid to a liquid. So it can be a liquid at 267, 268, 269. It's going to be a liquid at those temperatures. And it turns into a gas at 332. So here's the ticket. The temperature that we care about, STP 273, is somewhere in the middle. 273 would probably be like right here. So 273 for BR2 falls right between the solid and falls right between the melting point and the boiling point. Therefore, 273 will work. 273 BR2 is a liquid. So BR2 is your answer for number 54. Now, if you want to sort of double check yourself, tell me what's wrong. You can pause the video and think about this. What's wrong with I2? So why is I2 not an acceptable answer? Well, so I2, the problem is with I2 is that it melts at 387. So this temperature here is 387. At 273, it's already melted, okay? So at this point, or excuse me, it doesn't even melt until 387. So for I2, 387 goes here. 273 is down here, right? 273 is lower. So at 273, I2 is still a solid. Hasn't even melted yet. So I2 is not your answer either. All right, it's a tricky question, but BR2 is your answer. All right, the rest of these, hopefully we can sort of clean them up and get right into today's lesson. State in terms of intermolecular forces why I2 has a higher boiling point than F2. This is a question that we talked about. It's I remember a single lesson that we talked about a while ago in the physical behavior of matter. In this question, it's as simple as this. The stronger the intermolecular forces of attraction, the higher the boiling point, the more energy it takes to boil. So in order to answer number 55, you just got to put that into a single sentence, a single thought. So we're dealing with F2 and we're dealing with I2. In terms of intermolecular forces, why does I2 have a higher boiling point than F2? All you have to say is that I2 has stronger intermolecular forces than F2. That's your answer. I2 has stronger intermolecular forces of attraction than I2. Therefore, it has a higher boiling point. Simple as that. The stronger the forces, the higher the boiling point. The weaker the forces, the lower the boiling point. So you just have to say that I2 has stronger intermolecular forces than F2. Again, that's one of those easy questions that just looks really tricky. And last but not least, tough one, number 56. State what happens to the potential energy of a sample of NO liquid at 121 K as it changes to NO gas at constant temperature and standard pressure. All right, this is a little bit, again, I'd say these series of questions are tough. There are like 2 medium to difficult questions and then a difficult question. This is definitely difficult. So if you get it right, great job. Tough one though. So the first thing that you should do, if you lean on everything we've been talking about back when we were still meeting in person, you go and make the connections that you can. When I see potential energy and I see constant temperature and I see phase changes going from liquid to gas, when I see all those things, I'm thinking about this. I'm thinking about the phase change diagrams. Heating curves, or sometimes, maybe in the case of this question, nope, it is a heating curve. We're going from liquid to a gas. So I'm thinking of heating and cooling curves, right? Where you have, let's see, kinetic energy in this axis, KE, or your temperature, right? And then you have time. And as you heat a solid up, it increases until you hit the melting point, and then it melts. And then you heat up the liquid, and it keeps getting hotter and hotter until it starts to boil. And then it boils until it turns into a gas, right? And so that's what I'm thinking about. So what happens to the potential energy of a sample of liquid as it changes to gas at constant temperature? So once you read the question very carefully, you know that you're dealing with a liquid turning to a gas at constant temperature. So if you're picking out a line, you should be right here. This is the line that the question is asking you to make a connection to. Here I have a liquid turning to a gas at constant temperature. Okay, notice that here at this point, my temperature would be, according to the question, 121 Kelvin. And as it goes on here, as time passes, it stays at 121. The temperature is still the same. On this side of the line, the temperature is 121, and it doesn't change over to this side. Temperature is constant. That's what the question is saying. Well, what happens to potential energy? If it's a liquid turning to a gas, on the line here, kinetic energy stays constant and potential energy increases. For number 56, to get it right, you would have to say that potential energy is increasing. And that's it. But there's a lot of stuff you have to put together just to get to that. Okay, so which is my liquid at STP? It's going to be bromine, Br2. Why is I2, according to intermolecular forces, why does it have a stronger, higher boiling point? I2 has stronger intermolecular forces than F2. And number 56, potential energy is increasing. All right, I'm going to slide over here and move this on out. Just a little heads up, guys, as we sort of transition to the next slide. I know these do-nows, they take up a considerable amount of time, but this is your time to practice. This is your time to review. You know, you're looking at the Regents. If it all stays intact here and we have the Regents exam, you're looking at like less than 3 months. And we have a lot of work left to do. So this is your daily practice. So I hope you take these seriously and don't just skip through them. All right, we have again, I think a pretty easy day today. We have 4 objectives here. We're going to sort of smush together 2 lessons into one. You have to label all the AE arrows on a blank PE diagram, as well as identify all the AE values on a PE diagram. Then you're going to label the delta H arrow on a blank PE diagram, and you're also going to identify the delta H value on a potential energy diagram. And then hopefully you can explain verbally and in writing how you know that a PE diagram shows an exothermic or an endothermic reaction by using delta H as a justification. Sounds like a lot, but I think you guys will be all right. Here is your do now. Oh, sorry, your meme of the day. I'm starting to make my own. Now, I know that my videos, like I said, I originally intended my videos to be like 5 or 10 minutes long, and I know they creep up on 20 minutes at times. Most of the time, at least a third to half of that can be the do now. So, but I just want you guys to keep practicing these things. We get 45 minutes in class. And so it's reasonable to think that some of these daily videos, which are filling in for a class, could be around 20 minutes. So, I hope that you can find a half hour a day to sit quietly, put your headphones in, watch these videos from start to finish, and follow along in your notebook and really treat it like a class. I think the students that do that will be all right. Okay, so I hope you guys are doing that. I know it's funny to joke about. You guys probably fast forward through these videos, but I hope you do watch them because there's a lot of important material there. All right, yesterday, we talked about our potential energy arrows. You know that anything that goes from the x-axis to the bottom part of the curve is a PE arrow. So in red, that's the potential energy of the reactants. In blue, that's the potential energy of the activated complex. And in green, that's the potential energy of the products. So we learned those arrows. You need to know their value. So it's 40 kilojoules for the PE of the reactants. It's 100 kilojoules for the PE of the activated complex, and it's 20 kilojoules for the PE of the products. Now we're going to look at these other arrows. These are called activation energy arrows in blue and in red. And there's only 2, but I've drawn them in 2 different ways, and I wanted you guys to see both. Okay, so why don't you take a minute and tell me, this one here, these are your PE arrows. How are they different from these ones? What do you notice about them? And what are the differences? I'm going to pause the video, let you think about it, look at it carefully, then we'll go over it. Pausing the video now. All right, welcome back. Hopefully you had time to analyze these 2 graphs. I mean, the differences are hopefully pretty obvious. So first of all, the arrows for potential energy, the PE arrows, they go from the x-axis to the underneath part of the graph. In this case, these arrows do not touch the x-axis. In fact, these arrows only stop at where the potential energy of the reactants start, and these arrows start where the potential energy of the products start. And then they both go to the peak of the graph. Okay, so we have a different arrow here that sort of represents a different part of the graph with a different amount of energy. Secondly is to quantify these. If you start at 40 and you end at 100, you have to think what actual amount of energy is there. Well, you're gonna have to do some subtraction. Unlike these ones, since they start at 0 and they go to 40, it's just 40. This is 0 to 100, it's just 100. And this is 0 to 20, it's just 20. This is going from 40 to 100, which will be 60 kilojoules of energy. This one starting at 20 and going up to 100 will be 80 kilojoules of energy. So in order to actually quantify these values, you need to do a little bit of subtraction. Okay, so that's it. Those are the two arrows we're going to talk about. We're going to do a couple practice questions. Here is your definition before I explain to you what it is. And then we'll practice labeling the arrows and quantifying them. So pause the video, copy this down in your note. Okay, activation energy. Here's a little bit of the background behind it. Activation energy is the energy required to start or activate either the forward or the reverse reaction. So when you are going from left to right, from reactants to products, you have this set amount of energy that you need to overcome in order to get your reaction to progress. So I always use this roller coaster analogy. Before you go on the roller coaster ride, you have to get brought up all the way to the top. And then once you're at the top, then you have enough energy now from going up that high of a hill. You have enough energy to go all the way through the ride, follow it along here, and take the ride to completion. But you have to get pulled up over the hill. If you don't get to the top of this first hill, you'll never go through the ride, right? You'll never be able to go on the whole roller coaster. Think of it like that for the reactions. If you don't get the activation energy that you need, the reaction does not happen. Okay? You have to have enough energy to get up over the hill. And I'll show you what I mean. Let's look at this one. So here, we'll use most of these from left to right. The forward reaction is A plus B turning into C plus D. Let me keep all the colors the same here. So I'll use blue. So we're starting here. We have our reactants that have this much energy to start. The amount of energy that they need to get over the hill and to turn into products is this. So how much energy do they need? How much energy does it need to be able to get over the top of this hump? You need 40 to 100, that's 60 kilojoules. So if you give this reaction 60 kilojoules of energy, it has enough energy to get up over the top of this peak. And then the molecules, if you will, can go through the ride and turn into products. So if I give this 60 kilojoules of energy or more, they have enough energy to get up over the peak and turn into my products. Okay? If I only give them something less, like if I only give them 40 kilojoules of energy, it's going to stop about here, right? It doesn't have enough energy to get over the peak. They're just not going to, it's not going to react. It'll stay A plus B and we will not be able to form products. Okay? So that's essentially the philosophy here. And then the same holds true for the reverse reaction. Now with the reverse reaction, instead of going from left to right, we're going to be going from right to left. For the reverse reaction, if I want to turn my products back into reactants, now I have a bigger hill to climb. So well, how many kilojoules of energy do I need to get over the top of that hump? Well, I got to get up to 100, but now I'm starting with 20, so I need 80 kilojoules of energy to get over the hump. So if I give this 80 kilojoules or more, I've given the reverse reaction enough energy to go. If I don't give it 80 kilojoules, then the reverse reaction will not happen, and I'll just be left with products, my C plus D, and they will not go back into A plus B. Okay, the last thing I want to highlight really quick is the arrow location. You sometimes will see the arrow drawn in the middle of the graph somewhere. Sometimes you see it all the way off to the side. Notice that these two arrows, they show you the same value. They go from the same place. In this case, they go from here all the way over, right? And if I draw it here, it's the same thing. It's the same value, just drawn two different ways. You can see it drawn both ways. Back to this one too, same thing. You can see the arrow all the way over to the left, or sometimes you might see it floating around somewhere in the middle, but it still goes from 100 to 40. It still shows the same value. So just be on the lookout for that. All right, so what I'd like you guys to do is maybe take a minute, pause the video, sketch this all, and try to sketch where the AE, the activation energy of the forward reaction arrow would be, where the activation energy of the reverse reaction arrow would be, and then I want to know each value. So I'm going to pause the video and let you guys do that now. All right, we're back. Let me minimize that. That should work. Really quick. So if my activation energy of the forward reaction, my forward reaction is going to be here. So this is my arrow, my activation energy of the forward reaction. Notice we go from the PE of the reactants to the top of the graph. Okay. You could also have drawn it somewhere in the middle here like this. Same thing, shows the same value. Either arrow is fine. I just want you to get in the habit of seeing them both ways. So there's my arrow, my activation energy of the forward reaction. What is its value? Well, take the bigger number, 250 minus 50, it'll be 200. So it's 200 kilojoules. It takes 200 kilojoules of energy to get this forward reaction to go. Okay, I'm not gonna, yes I am. I will write the label. It takes 200 kilojoules to get this reaction to go. On the other hand, the activation energy of the reverse reaction. Here I'm going from the potential energy of the products to the top of the peak. Ooh, sorry guys, this is not as easy as it looks. You can see the arrow written over there. That's where I like to draw the arrow, but once in a while you see the arrow floating around in the middle of the graph somewhere else. You could see it drawn over here too. Doesn't matter. It still shows the same spot. We're going from this line here to the top of the graph, right? Now, what is that quantity of energy? Well, we are going to 250, but we're only going down to 100. So 250 minus 100 will be 150 kilojoules of energy. So that is the quantity of the activation energy of the reverse reaction. Okay. At some point, you will be responsible for sketching all the arrows, knowing all the locations, and knowing all the quantities. And there are 6 of them. So you've learned 4. Potential energy, actually 5. Potential energy of the reactants, potential energy of the activated complex, potential energy of the products. Now you have the activation energy of the forward reaction and the activation energy of the reverse reaction. That's 5. We got one more thing we're going to learn in a separate lesson. Okay, but this is what I asked you guys to do for that slide. All right, almost done. We're going to finish this up, and then I'll give you guys an exit slip, and we'll take, it says a break here, but I'm going to break it up into a separate lesson because this is going to get, it's getting a little heavy for you guys, so I get it. All right, try one more like this. Again, sketch and quantify the activation energy of the forward reaction and the activation energy of the reverse reaction in this graph in your notes, and then we'll do the exit slip, and we'll shut it down for the day. All right, here we go. Almost done. So again, really quickly now, I will do this in red. The activation energy of my forward reaction will go here to here. Okay, and its value will be 100 minus 40, which is 60 kilojoules. My activation energy for the reverse reaction will go from here to here. And it's 100 minus 20, which is 80. This looks strangely familiar, like maybe I accidentally copied this twice from earlier in the lesson. Either way, you get it. These are where the arrows are. This is what they're called, and these are what their quantities are. All right, that's good enough, guys. Here's your exit slip. I will post this on a Google Doc, and I'll let you guys watch the video and go through it. I will, after I'm done with this, I will make a second lesson for a separate day about the last arrow that you need to know, and then we will they'll move on. So I'm actually going to, just for the sake of it, go back to our objectives for the day. The goals were to label all the activation energy arrows on a blank PE diagram and to identify all the activation energy arrow values on a PE diagram. We've done that. I'm going to do these next 2 objectives in a separate lesson. All right. All right, guys, good job. I look forward to seeing your responses in your exit slip. Have a good day.